Hello everyone, hopefully you're doing well. In this video, we're going to continue with chapter 8, Exponential Astonishment. After we took a look on section 8A, growth of linear growth versus exponential growth. In this unit, we will try to convert between growth or decay rates and doubling half times because we know exponential growth leads to repeat doublings and exponential decay leads to repeat halvings. So in this section, so you see we're going to take a look on doubling times and half time. In most cases of exponential growth or decay, we are giving a rate of growth or a decay, usually as percentage rather than the time required for doublings or halving. So what we mean by that, you know, doubling and halving. So halving means half, right? Doubling means you double. The time required for each doubling in exponential growth is called the doubling time, right? So that's what we call them. Um, you know, um, uh, the required, for example, the doubling time for the magic penny. Remember, we covered this one was 1 day because your wealth doubled each day. The doubling time for bacteria in the bottle that we saw also in the previous video session, unit 8A, we said that it was 1 minute. So it all depends of what you want to do. So the times required for each halving in exponential decay is called halving time. You have doubling time and halving time. So at some point, we can write a general formula. If we let t, be the amount of time that has passed, and capital T double for the doubling time, it all depends of what you want to do. So after a time t, small t, an exponentially growing quantity with a doubling time of capital T double increase in size by a factor of t power 2 power small t divided by capital T double, the new value of the growing quantity is related to its initial value, at t equals 0, by this new formula. So this formula here gives us the new value. So, it's the size of a population T, after T time, if it's initial population time T power 2 power T divided by capital T double. So we're gonna have a chance to consider all of these formulas, whether the doubling time. We're gonna do a few examples, but one thing you need to remember, if we use doubling with compound interest, remember what compound interest is exactly. So if we know future value, or if you consider it as populations, either population, we're gonna say compound interest or populations. We know population at time t is equal to initial population times RT. Okay, so R is the growth rate, or growth rate, and T is a period of times. So that's a formula for it. So how long it would take for this population to double? I mean, initial population to double. How long will it take for P to equal to P? So that means double the initial population. So if you do 2P nuts equal P nuts E R T, remember I say R is the growth rate. So you see here, if you divide both sides by peanuts, okay, you realize you're gonna have 2 equal E R T. Okay, now for those of you who remember, you complete some logarithmic functions. Remember logarithmic functions, ln, log, or ln, the natural logarithms. So we said if you have ln a times b, it's the same thing saying ln a plus ln b. If you have ln a divided by b, it's the same thing as having ln a minus ln b. If you have r, okay, ln x power r, or I'm gonna say ln a instead because we've been doing so. Ln a power r, you see there is a power. You can bring the exponent to the front, and then you have ln a. That's very important to see the product rules because we call this one product rules, product rule. We call this one quotient rule, quotient, and we call this one power rule. Okay, we have all three like this. Now, I mean, I'm showing you all of this just for you to remember how we're gonna solve this for t because we're looking for t. Two equal EDR of t. Now, other properties to remember about logarithms. We said ln e is natural logarithm. It's equal to one, and ln one is equal to zero. So those are very important to keep. Now. If we take the ln of both sides, because when we want to solve for an exponent, we can solve for the ln of both sides. So if we take ln from both sides like this, now ln2 stay ln2, but here we can bring the RT to the front and ln E. So if we use the power rules property, so ln2 is equal, remember, LRT times 1 because we said ln E is equal to 1. So ln2 equal RT. If we divide both sides by R, so we have ln2 over R equal T. So at some point, you can say this is the times it takes for a population to double, or this is the times it takes for interest to double. So it all depends on what you want to do. But if you want to find out how long would it take for an investment to double, for a population to double, it should be ln2 over the growth rate or the interest rate. So it all depends on where you are with it. Let's do a few examples very quick because we're gonna have to solve all of this. If you look at these examples, all right, let me grab my calculator then. Uh, all right. So if we go with the first examples here, they said um, for each exercise, give a doubling time for an exponential growing quantity. Answer the questions about the growth of each. So I'm gonna usually I do one or two for you to continue. In the first examples, it says the doubling time of a population of fruit flies is 12 hours. By what factor does the population increase in 36 hours? So if you do it, 36 hours for t equal 36 hours. So we're gonna go with doubling in 36 hours. So we said in 36 hours, the fly population would increase by a factor. You remember that we said we just covered the the factor. Um, let's go up there to show you the doubling factor. So we said after a t time an exponential growing quantity with a doubling time of t double increase in size by a factor of 2 power t small t. So we have two, I mean, we're gonna call it, let's call it a doubling factor. We said uh, um, with a doubling factor of t, so it will increase by the factor, increase factor. We said is 2 power small t divided by capital T double, right? So if we do that for these examples, that would be because they said the doubling times of a population of fruit flies 12 hours. So for us, is that we have capital T doubling, double is 12 hours, right? So that's what happened. Now for us, uh, that factor would be 2 power T over capital T double. So that would be 2 power 36 over 12. What is 2 power 36 over 12? Would be 2 power 3 equal 8. So since, because now what we do, we know this is the factor of it. Now, remember, we were talking about hours for part A. So that would be our first answer. But they said in 1 week. Remember, how many hours? Because we're working with hours, because you cannot divide by one, okay? So we cannot say we have small t. So if small t is equal 1 week, you know that's equal 7 days times 24 hours. So 24 hours. So if you take 7 days times 24, it gives you 168 hours. So we need to have the same unit. So at that point, we're gonna have 2 power 168 over 12 when we do it for 1 week. Okay, remember, first of all, they said do it for 36 hours, then do it for 1 week. So in this case, it would be 2 power 14. So if you do 2 times 2, you do this factor 14 times, it's gonna be 16,384 in 1 week, right? In 1 week. Right? The first one is in 36 hours. So this one in 36 hours. All right. So hope you can use these examples. As I said, I do one or two or three, then you can continue on your own. I can take any of the other ones, like if you decide to go with B, the doubling time of a city's population is 20 years. How long would it take for the population to quadruple? Yes, so this and how long would it take to the populations to quadruples? The population will increase by a factor of 4 because quadruples, you know, um, if we go with a different for B, the doubling times of a population's of a city's population is 20 years, right? So you have the doubling time. So that means for us, T double is 20, right? How long would it take for the population to quadruples? So, I mean, having it 4 times, right? So, it's like 40 years, right? Because we're gonna consider it as because quadruple now he's double. If doubles is 10 is 20, that means the initial one was 10, right? Now if you do it 4 times 10, for us the small t would be 40 because how long is taken for quadruple. So if we do the factor 2, small t over time is double, would be 2 power 40 over 20. 2 power 2 is 4. So how long would it take, right? It would take 4 years to quadruple, all right? So we said that I mean it's not 4 years, but that should be the factor. That's the factor because we're looking for the factor. The factor is one element that we need to multiply with the initial value so we can find the new values. But we just try to practice the doubling times, right? Capital T doubles and also the times it takes to double. So that's very important. Hopefully, you can use these two examples to do the other ones. Now, in 2017, the estimate population, that's another examples that we can do. We're talking about these exercises. Okay. So we said in 2017, okay, the population, the estimate populations was 7.5 billion people. Use the giving doubling time to predict the world populations in 2027, I mean 10 years later, 67 and 2117, 2117. Assume a doubling times of 40 years. Okay. Now, what they ask you to do for these particular examples is really to verify the times it would take to double. Remember, for these particular examples where we said we're gonna do it for 40 years, the year 27, right? If we go with A, let's go with A. So the year 2027, pretty soon, of course, is 10 years later, is 10 years later, okay, than 2017, right? When we started, than 2017. So if you agree with that, I'm fine with that. So the population would be, remember in 2017, in 2017, population was 7.5 billions, right? So now they said predict predict to predict it. So meaning the doubling time, remember they give you the capital T doubles here is 40. So the difference here for time, we know is T equal 10. So we know T equal 10, right? And using the previous formulas you see here, new value, remember new value is equal initial value times the factor, T over capital T double. So meaning 7.5 billion, that's the initial value, times 2 power 10 over 40, right? So if we do that, we find the new value to be 8.9 billions. So that's something you can verify. Pretty sure, pretty soon we're gonna be 8.9 billions of people. So if we do that, remember this is for 27, but what if you do it for 2067? So in 2067, so what would be T? You can count from 2017 to 67, so small t would be 50, right? So if you said small t is 50, now new value using the same formula from 2017 would be 7.5 times 2 power, what? What is small t? Small t is 50. And double time is still the one that they give you in the formula. So you know the population by 2067 would be 17.8 billions of people would be on the earth if nothing is done by 2067. Now, they said what's gonna happen in 2117, like about a century later. So in 2117, what would be T? T would be 100, right? It's gonna be 100 years. So meaning the new value using the same formula would be 7.5 times 2 power 100 over 40. Remember, we still using the same doubling time of 40. So you're gonna do the same using a doubling time of 60. But now every 40 years the population is double, so that's why we're using this factor instead. So meaning if nothing is done to prevent the population from growing by in 1 century, 100 years from now, we're gonna be 42.4 billions of people, knowing the maximum capacity for the Earth surface is about 12 billion for everyone to live peacefully and can breathe peacefully in this planet. So very important to pay attention to the global warming as the population keep growing. So that's an example that we could use. Other questions to ask is about the approximate time formula. So the approximate time formula, there is a rules, very important rules that we consider. We call it, the 70 rules. If, it all depends on what we do. It's a formula in which the doubling time is approximately 70 divided by the percentage growth. Works whenever the growth rate is relatively small, less than a 15%. So it's often called the rule of 70. We can use something to verify it. So this approximation, as we said, works best for small growth rates and breaks down for growth rates over about 15%. So this approximately doubling, it all depends of where we do it. As we said, uh, you know, there is a table that I wish I could share with you, but you can even Google if you want to growth of a prairie dog community. You can try it, and it would explain this to you because we did that. If we consider an ecological study of a prairie dog community, so if you Google, you would see that one. This community contains 100 prairie dogs when the study begins, and researchers determined that the population is increased at a rate of 10% per month. So that is each month the population goes 110%, right? Or 1.1 times its previous value. So we said, it's usually the way we do it. As I said, this table, you can see it. So the population nearly doubles to 195, after 7 months if you do that. So that's why we come with this roughly 7 months doubling is related to the 10% growth. So if we use this rules, remember we call it double times is 70%. So let's try it in this particular examples where we said a community of mice begins with an initial population of 1,000 and grows by 20% per month. Make a table similar to the one, unfortunately, you don't see it. Make a tables that shows the population for each of the next 15 months. Based on the table, find the doubling time of the population and briefly discuss how well the approximate doubling time formula works for this one. So what they want us to do here is to verify if we can eventually use that formula we talked about. Okay, we can try. I'm gonna try to see if it's possible. But the problem, they said we must do it for 15. Okay. So what we're gonna do from here, remember we have the formula. So if I have a tables, because they said the community of months begins, if we put the months, I'm gonna try to write as small as possible. And we put the population, the access to construct a table. Okay, let's do it that way. A population. Now, you know, initial population at time t equal to 0, we have 1,000 mice and grows by 20%. So every time, I told you already, it grows by 20%. I gave you an examples of how to find any future value. Take the present value, you multiply it by 1 plus the rate power t, right? So for examples, after the first month, if you do the first month, if t equal 1, you can just take your initial population, 1,000, times 1 plus the rate is 20%, okay? Power t is 1. So at this point, 1.1 times 1,000, it gives you 1,200 for the first month. Now you can do the second month, you do the same, but now you understand is 1.2 power 2. Okay, that would give you 14.4. If you do 3, you still have 1,000 times 1.2 power 3 because time would always be the same, 1728. So not the time, I mean the percentage. All right. If you do 4 months, for 4 months, we're gonna have 1,000 times 1.2 power 4. Okay, 1.2 power 4, we're gonna have 74, etc. So what I'm gonna do, because you know how to do it, I'm not gonna spend the whole time. I strongly advise you to fill it up on your own because 5 give you 24. 88. Now we can go all the way down to 15, right? When you go to 15, still the same thing. You take 1,000 times 1.2 power 15 because we do it for 15 months. And you end up with, 15,407. So you start with a population with only 1,000 mice in exactly 15 months, 1 year and 1 year and 3 months, right? 1 year and 3 months, you end up with 15,407. So they said make a table that shows us the population for each of the next 15 months. Based on the table, find the doubling time of the population and briefly discuss find the doubling time. Okay, so we need to find the doubling time. As you can see, we said we can use the t doubles because they said use the t doubles. That's a different ways we can find the t doubles. We said that should be 70 over P. So now what is the percentage? All right, you can find how long it takes to double. You see, when you start with 1,000, so it goes 2,000 between 3 months and 4 months, right? Between 3 months and 4 months is double, right? And if you try again, you can see it's gonna double again at some point 7 months, right? Because if you do 2,000 after 7 months, 8 months, between 7 and 8, you're gonna have it doubled again. Okay, so we said because the population after 4 months is 2,074, which is a little bit more than twice the initial population of 1,000, the doubling time is just under 4 months. So the approximate doubling time formula claims so approximate doubling the approximate doubling time formula claims that yeah, I'm hoping you can listen to what I said as well because my handwriting is really terrible. I apologize for that. So if you do, remember it's 70 over P. And what is P again? Remember, the rate. I mean, I call it in this one rate. I mean, for us, it's like rate is 20%, right? It's 20%. So because it's 70%, so 70 over 20, that gives you 3.5. Okay. So it gives you 3.5 months, which is not perfect agreement from what we could discern from the table, right? Uh, this is due to the fact that the approximately doubling times doesn't work as well as on the rate is greater than 15%. So remember, if it's greater than 15%, it's hard to do it the way we want it. But at some point, you have an idea what it would look like. Okay, now let's try another examples because again, here they said use the approximate doubling time formula rule of 70. Remember, T double we said is 70 over the percentage they give you, usually under 15%. Discuss whether the formula is valid for the case. So if we go with A, what they ask you to for this one, they said a city's population is growing at a rate of 2.5% per year. What is the doubling time by what factor? I mean, what is the doubling time? Sorry, that's the first questions they ask about this one. So doubling time, very easy. We're gonna use this formula because they said use 70 over P, which is 70 over what is P in this case? P is 2.5 because this one right here is P. Okay, so the doubling time for this one would be 28 years. Okay, a city's population is growing at this rate. To double that population, it takes 28 years. What is the doubling time? We find it. Now, the next question, the population would increase by what factor? Remember, the population would increase by what factor? Remember, the increase factor would be, you know, remember we said population equal population initial plus one time plus weight power t. Okay. So, um, you know, uh, by what factor will the population increase in 50 years? So if t equal 50 years, this is the factor. The factor would be 1 plus the rate power t. So that would be 1 plus 0 point, okay, 0.0254 for 2.5% power 50. So we have 1.025 power 50. So that would be 3.45. So this is the approximate doubling time formula. The questions is by what factor? Factor. Okay. Now, you see by what factor, that's what I show you here. And this is said, discuss whether the formula is valid for the case described. What you can say here, the approximately doubling time does a reasonable job. So I think definitely is reasonable because it's I mean, first of all, it's under 50%, so which is great. Okay. So usually, I do want examples and I leave one for you following the same types. Now, Other topics to cover in this video is exponential decay and half-life. Very important. Exponential decay occurs whenever a quantity decreases by the same percentage in every fixed time period, right? Like, let's say mm, it decreased by 20% every year. That's an example. In that case, the value of the quantity repeatedly decreases to half its values, which with each halving occurring in a time called half-life. So that's why we call it half-life, right? After a time t, an exponentially decaying quantity with a half-life time of t half decreases in size by a factor. We give you a formula for it, okay? Um, by a factor of 1 over 2. Remember the doubling time. Remember t double, okay? I mean, we have that factor. So we have that factor of small t over capital T double, right? But now we're gonna do 1/2. So for us, the decreasing in size by factor of 1/2, uh, 1/2 power T half, okay? So make sure you write it correctly. For us is 1/2 power T over T half. Now, we're not gonna say T double, but we say T half. The new value of the decaying quantity is related to its initial value. You will must do the same examples we did before, previously. Remember, here, if we go back, you see that formula here gave you the doubling time. Now we're going to focus on the, did I skip something? No, I didn't skip, sorry. Okay. We're gonna focus on the half, okay, decay instead at t equal to 0. So this is what we're gonna have. Let's do one examples very quick again because we're gonna come back to rules of 70 later for halves. We said in each exercise, give a half-life for an exponential decay quantity, answer the question. So that's what we're gonna do for this one, and answer the questions about the quantities decay. So we said the half-life of a radioactive substance is 40 years. If you start with some amount of this substance, what fraction of that amount will remain in 80 years? So first of all, an exercise like this one, you need to read it multiple times. But now, if we go with A, they said, what's gonna happen after 80 years? After 80 years. So the half-life of a radioactive is 40 years, right? The half-life is 40 years. If you start with some amount of this substance, what fraction of that amount will remain in 80 years? Remember, 80 years at that point, what 80 years represent, we need to verify from the previous formula. Remember, is T. We said that factor for us, we said it's 1/2 power T over T half, right? So if you have the factor 1/2 power T over T half, remember capital T at the bottom. Now, if that's ever happened, what we're gonna do here in these examples is 1/2 power Now the t we got is 80. It must be 80 because the half of 80 is 40. So what they give you here for us, this one here is t half, okay? And this one here is small t, okay? So now putting this together, as you can see, it would be 1/2 power 2. That gives you 1/4. So that's 0.25. Now, after 120 years, so that would be something again, So if you do after 120 years, again, you're gonna have 1/2 power 120 over 40 because 40 is the half, right? So if we do that, then answer would be 1/2 power 3 would be 1 over 8 equal 0.125. So we answer the question for part A, and if you want, we can either do part B, or I can leave them for you to enjoy. But look, if they said the current populations of a threatened animal species is 1 billion, but the population is declining with uh, you know, declining with a half-life of 25 years. So how many animals will be left in 30 years? So if, again, those type of questions, we can look at them and answer right away. We can either answer those questions right away if we want to, not all the time, okay? So, but they said what's gonna happen in 30 years. Again, for these examples, the current population of a threatened animal species is 1 million of it. So remember the questions here. You need to do new value equal initial value times 1/2 power small t over capital T half. So that's what we're gonna use as a formula. For us, we know using the formula new value equal initial value times 1/2, because we're talking about decay, small t over capital T half. Now, our new value initial value, remember, they said the current population of a threatened animal species is 1 million. So let's suppose we put 1 million here, okay? Times 1/2. Now, what is small t? The first question is to identify which is small t. So small t, how many animals will be left in 30 years? So 30 would be small t. And we know already the year for half-life. Do you get the half-life of it? Because they said um, the current population of a threatened species, but the population is declining with a half-life of 25. Okay, so if we take it, it's declining at a half-life of no, I think I make a mistake here. It was supposed to be 24. Let me fix it. 24 right there. Okay. So that would be 24. Okay. So 24 then, so doing this in the calculator, divided by 24, that gives you 420,000 animals. Okay. Okay, 420,000 animals. Now, this said what happened in 70 years? In 70 years, again, in 70 years, the new value always take the initial value, 1 million, times 1/2 of 70 over 24. That's half-life because they already give you half-life. That give you 132,000. So we said the current population of a threatened animal species is 1 million, but the population is declining with a half-life of 24 years. How many animals would be left? After 70 years, you go from 1 million to only 134,000. So that's definitely declining over the times, very quick. In less than 100 years, knows that there will be no more of this species anymore in that area. So very important to verify that. Now, because you do these rules also, we can apply it. Approximate half-life for applying the 70 rule. The approximate doubling time formula, the rule of 70 we found earlier works equally well for exponential decay if we replace the doubling time with the half time and the percentage growth with the percentage decay. So very important. So for a quantity decaying exponentially at a rate of p% per time period, the half-life is approximately equal, um, um, you know, 70 over p. This approximation works best for small decay, of course, if it's less than what we just said. Okay, again, we have one more exercise, or we're gonna do only one exercise because we have two of these. We're gonna do one and leave one for you. Use the approximate half-life formula. Discuss whether the formula is valid for the decay for the case described. So what we're gonna do, we can use this formula to do it. What they said, the Great African Elephant Census completed in 2016 found a total of population of about 350,000 African elephants. Researchers conclude that the population was decreased at a rate of 8% per year, primarily due to poaching. What is the approximate half-life for the population? So that's the first thing we're gonna ask you to find. Then based on this approximate half-life and assuming that the rate of decline holds steady, about how many African elephants will remain in the year 2050. So again here, we know that's a different type of exercises, but we still can use the rules because they said, can we use the half-life where T double, or not T double, we call it T half, 70 over PP in percentages. Now, we know they said the approx the you know the Great African Elephant Census, the Great African Census in 20, found a total of about 350 elephants. Researchers conclude that the population was decreased of a rate. For us here, P is 8%, right? So if we use T half-life, because that's what they ask you to find, we know is 70 over P. So that should be 70 over 8. So if you do 70 over 8, it takes like about 8.75 years to break it into half. So now that's the first part of the questions. The second part of the questions, is gonna take this one to for the half-life, the time to half it, right? Now they said based on the approximate half and assuming that the rate of decline holds steady. Uh, about how many, that's in what is the new value. That's the things you need to find. You need to find the new value. If you know the old value, so initial value. Right now, we know the rate. We know the rate. So what we're gonna do is because we're gonna subtract instead of plus, minus the rate is decay, all right, power t. Now the new value, the initial value 350,000. One minus the rate is 8%, 0.08. What is t in this case? Because in 2050, from 2016 to 2050, all you need to do, you do 2050 minus 2016, you know, from 2016 to 2050, T is 34. So we're gonna say it's 34 here. So new value would be what? If you 350,000 times all of this and you plug it, there would be only in 34 years, if it decay at a rate of decrease, but at a rate of 8%, there would be only 21,000 elephants left in 34 years. Okay. So using the half-life formula, if you want to use the half-life formula instead, so I use first of all, let me put this one a little bit higher. Based on the analysis of holes, about how many, if we use this formula, it says you have only 21,000. But if you use this formula I just gave you, where is it again? Not here. Okay, new values. If you do this one instead, let's see how many you're gonna have using the half-life formula. Right? So now what you can do with this is take the 350,000 times 1/2 power. Remember T is 34 because that's the times you have over T doubling. We already find it. This is the T. T half. That's T half. Remember that. Okay. That's T half over 8.75. So answer, when you do that, that would be 24,000. Oh, about 4,000 more elephants. So using this the approximate life formula, there's is somewhat reasonable job. So we are pretty close. Remember, the first one is the exact one, but if we use the 70%, it gives you 24,000, but 70% is kind of doing an excellent job. Okay. All right. Now let's conclude these sections with exact formula for doubling time in half. We can do that. I told you at the beginning, if you want to find the times, it's also be ln2 over r. So that's somehow you can use. Or for more precise work, because the approximately doubling time and half-life formulas are useful because they are easy to remember. But for some reason, for more precise work or for rates of growth or decay, where the approximate formulas break down, we need the exact formulas giving giving that answer. Very important. So these formulas use the fractional growth rate. R for us is the percentage over 100 with R positive for growth or negative for decay. You need to remember that. So for an exponential growth, quantity exponential growth. If it's growth, it's log base 10. Usually we don't put log base 10, we just put log 2, base 10 2 equal log base 10 1 plus R. Or if it's half, you use the negative sign, but still the same formula. So if it's growth, you use positive. If it's decay, you use negative. We're gonna go over these examples very quick, probably do one extra examples or exercises to make sure we are on the right track. Let's do A. We said that you know inflation is causing price to rise at a rate of 6% per year for an item that costs $600 today. What will be the price in 4 years? Okay, very important. That's good. Very important. So inflation is causing prices to rise at a rate of 6% per year. Okay. We must go over again and make sure this is the correct one. Okay. Um, all right. Inflation is causing price to rise at a rate of 70%. Because it said compare the doubling times found with the approximate and exact doubling times formulas. Then use the exact doubling time formula to answer the question. So we must, uh, you know, do it. So if we use because it said inflation is caused price to rise 6% for an items that cost 60% today, $600. So what would be the price in 4 years? Um, you know, I believe we're gonna do T doubles, right? For this one, we said the approximate doubling time. Let's go with A. Approximate doubling time, T double, using the 70 rules, 70 over P, which is 70. What is P? P here is 6% over 6. So if you do over 6, that's 11.7 years. So it would take 11.7 years to go from 600 to 1,200. So that's what we said about this. So the exact doubling time, if we use the exact doubling time, the formula we just see here, if we use that one, right? If we use the exact, okay, uh, right? Exact doubling time, right? So if you do t, no, no, that should be doubling, not the negative one. That's half because we double. Let's go back. I take the double one, right? I'm gonna come back here and do pass. Let's do the double with the positive side. The exact doubling time would be log 2 over, remember, I don't need to put the 10, okay? Log 1 plus the rate, which is 0.06. So when I do that from a calculator, you need to double check with your calculator. We find 11.9 years. Oh my God, they are very close. If you want to round, both of them would round to 12. So because we can find 11.9 years, so the price of 600 I mean, it would double, around the same thing. But they said, what will be the what will be the price be what will the price be in 4 years? So remember the formula to find the price in 4 years. If remember you do new value in 4 years, okay, price would be, take the new value, the initial value, 600, and remember you can double it. Double mean, you take your times two. Remember you have new value equal initial value times 2 power small t over t double. And we already know what t double is. But small t is 4, of course, because t is 4. And capital T double, we computed already. It's 11.9 or point 0.7. We're gonna go with point 0.9 with the exact. So 11.9. So in 4 years, what would be the price? The price would be 757.42. So note that is this the sensor is using the rounded value for the exact doubling. If you use all the digits, your calculator should be like maybe, bigger than that. But at some point, we answer the first questions, and I'm hoping I teach you enough in this video to do all the other examples. In a different video, we're gonna come back with HC real population growth. Hope this one helped. I'll see you in a different video. Take care.